Hello, everyone. So this module will focus on selecting earthquake ground motions and scaling them for performing nonlinear response history analysis to understand the seismic behavior of structures. We have four kind of learning objectives with this module, and with this kind of first background video, we'll kind of hit some of these, especially the first three, and then leave the next video for an in-depth example that would use the SimCenter EEUQ the tool to perform kind of most of the work for selecting ground motions for specific buildings, run linear response history analysis, and then we will use Google Colab to do further post-processing to interpret the results and come up with an understanding of the seismic performance of a steel moment frame. So the learning objectives are the ones that you see here. Basically, we want to introduce the nonlinear response history analysis concept in very general terms. No, we don't plan to go super in-depth, but convey the main points of this type of structural analysis. We also want to show the general workflow for performing these types of analysis, what are the activities that one needs to do to perform this type of work. And then kind of touch into some important details about ground motion selection and scaling criteria, all of that before kind of introducing the example that's discussed in the next video. So the motivation for this is that it kind of relies on this to recognize, right, really recognizes that most extreme demands on structures vary with time, right? So most of if not all of the demands of a structure related to live loads, wind, earthquake, rain, tsunami, wave action, all of those change with time, which means that they are dynamic loads. And we typically, when we are designing structures and analyzing the behavior, we typically simplify them as static forces and typically kind of try to get the maximum value in certain time frame of those loads to come up with a suitable design or understanding of the building. But all of that is kind of overlooking the real dynamic aspect of the problem. So what we will argue here is that an accurate simulation of the dynamic response of structure would kind of first enable safer designs, because there's less likelihood of ignoring some dynamic aspect. And that's why the example you see on the figure towards the right of this slide is the Millennium Bridge in England that had significant issues due to vibration when it was first opened in the beginning of the 2000s because of that precise problem. We can also reach cost-effective projects because we want kind of use some conservative assumptions that are typically part of the simplifications done in design. We will have a more reliable performance. We could even be able to quantify performance if we quantify the performance, the response of a structure as it is. And we can also make sure that the structure is functional and comfortable. And that's kind of one of the issues with this footbridge, that it wasn't really a threat for safety, but it was really uncomfortable to use because of the excessive vibrations. So what's the difference really between a static and a dynamic analysis, right? So the first thing that we need to understand that's different is what's the goal, right? The goal in a dynamic analysis is to quantify the response of a structure subjected to an external demand that varies with time, right? That's the same goal for a static analysis, just that the load in a static analysis doesn't vary with time. It's just fixed and constant, right? Doesn't change with time. So that's the main difference. So you're all familiar with static analysis, most likely, where, for example, if you take a single degree of freedom structure, for example, like this, when you have two columns and a infinitely rigid beam, the only degree of freedom is lateral displacement, so movement of this mass on top to the left and right. In that case, if you have a static load applied on the top, on that 1 degree of freedom to pushing the structure to the right here, you have a 1 displacement, denoted here with U, and you will have only forces of the structure can counteracting that external force that are developed in these two columns here. That Fs is the force of the structure that goes against the external force, and then the equation of equilibrium in that one unique degree of freedom is very simple, and it's just that the internal forces of the structure equal the external forces applied to the structure. Well, in a dynamic case, it starts the same way, right? So you have an external force that now changes with time, and note that we are kind of making that explicit here, which kind of indicates that the internal forces that the structural elements develop also change with time. But on top of that, we got a couple other terms that rise from the equation of motions from the basic classical physics from Newton, right? When you get an internal term and not internal, but an inertial term that pops up because of the nature of time changing of the force, of the external force, and you also have a damping component, right? Because those vibrations somehow, when the external force it's removed, those vibrations eventually stop. And the only way that can happen if the system can send energy out or loses energy in the process. And one way we can simulate that loss of energy in the process or in the system is by having a damping force, or that is typically sort of depicted with this dashpot with FT, right? So basically we have two more forces in the dynamic equation of motion, which is the inertial term and the damping term. So that means that our equation of equilibrium becomes not only Fs on the left side, but also the damping and the inertial force. In the context of ground motion, so basically what happens is that instead of having a force applied on the degree of freedom that changes with time, you have a motion, right? And we'll touch on that in a second. So let's kind of simplify this equation to make it a single degree of freedom, right? So like 1 degree of freedom, how would this force, this equation of motion looks like? So basically the inertial term is just the mass multiplied by the acceleration of that degree of freedom. The damping becomes, one way to simulate damping is using a viscous assumption, where we have the damping force be proportional to the velocity of the motion. So we got a damping constant multiplied by the velocity of the motion, and then the internal force of the structure, kind of the deformation that happens in the structural members if we are linear elastic, is just the stiffness multiplied by the displacement. And this is really important to highlight, is linear elastic. And that equals the external force, right? Again, this is not yet a ground motion problem. This is only a dynamic problem. You have an external force applied to it, right? So that's when we have all of our components. Now, if we have, again, a single degree of freedom system, we can simplify this equation a little bit and play with the terms to identify that we can define the vibration response of a single degree of freedom with only two parameters. Only, say, the structural period and the damping coefficient, right? The damping coefficient being this symbol here, and the structural period that relates the mass and the stiffness, right? If you kind of take this equation, divide everything by the mass, and then work out the terms a little bit, you can get to this equation of period that has physical meaning. And that's really interesting, because what it says is that if you leave that structural system, right, that single degree of freedom system, and you let it vibrate freely, then the time it takes from crossing one, from one complete oscillation, basically, crossing it here, go all the way to the negative side, go all the way to the positive side, and crossing it again, that time, it's exactly the one you can compute based on the mass and the stiffness, right? So you need only two parameters, period and damping coefficient, to describe the vibration of a single degree of freedom. And now what happened when you have a ground motion, right? So we instead of having an external force that was applied on your degree of freedom, you have the ground moving. Now, when you have the ground moving, you don't have an external force. So your equation of motion becomes just the inertial term, the damping term, and the structural deformation term, all that equals zero because there's no external force. The catch here is that the inertial term has two pieces, has the acceleration that's developed relative to the ground, and the acceleration of the ground itself, right? So the total acceleration that it's subjected to the mass of this structure is the summation of the two, the relative acceleration and the total acceleration. So what that means is that you can kind of trick the system and make it an equivalent system of an external force applied to a fixed space structure, right? So instead of saying, so you do mathematically, it's just like you take the mass multiplied by the ground acceleration and send it to the other side. But physically, what that means is that you're saying, well, instead of having my building moving the ground, I would assume my building is static. It's just fixed on the ground. The ground is not moving. But instead, I have an external force that equals minus m multiplied by the ground acceleration. And that's like an equivalent system with a fixed space. That is kind of helpful because then you can use the same approach that we have just seen for external dynamic force to solve the ground motion problem. Right, so in that case, this is the case. We have fixed the base, and in the same location is not moving, and now we'll have this external force going against the direction of displacement. Now, it's interesting then here to understand or to at least inspect what is the effects of the different pieces of this equation of motion. So if I go back here, I mentioned there are two important parameters that define a single degree of freedom: the period and the damping ratio, excuse me. So if we look at the vibration period, which is really important for all of this analysis, you will see in this slide, you'll see why. Basically, we take a single degree of freedom structure and we subject it to a ground motion recorded from our previous earthquake. And then we assume two different vibration periods. One that's 0.5 seconds, so that's what it takes to do a full cycle, or 2 seconds, right? 4 times that value, from 0.5 seconds to 2 seconds. And here, you're just plotting the displacement time history, the displacement response of that degree, of that single degree of freedom with the different damping, the different period. And you can clearly see the difference, right? The lower period structure kind of moves a lot faster, right? Roughly, crosses 4 times, has 4 cycles before the longer structure, the one with the longer period, the more flexible structure, has only 1 cycle. But then the more flexible structure, the one that has the longer period, it takes longer to move from one side to the other, moves more, right? Moves more for the same ground motion. That's interesting to keep in mind, right? This longer period, which means either higher mass or lower stiffness, it's in general terms, it's a more flexible structure, takes longer to move, it also moves more. In this example, right, compared to the structure that has a lower period, that could be because of lower mass or higher stiffness. Now, we can summarize the effect that a ground motion will have on many different single degree of freedom structures if we use or construct a figure that's called the response spectrum. The response spectrum is just a plot that will show you what's the maximum value of the response for the same ground motion, but affecting the structures with different period, right? So in the horizontal axis, you have the period of the building or the structure, the single degree of freedom, always for single degree of freedom. And in the vertical axis, you have the maximum displacement, right? And then, so basically what that's saying is that you're taking a building with 1 period, subjected it to the ground motion, solving the equation of motion, and only taking the maximum value of the displacement, the absolute, actually, the maximum of the absolute of the displacement. So you see here, it was negative. It takes the value as positive and plot it here. For this one, then, take the next period, do the analysis for the same ground motion, solve the equation of motion, you get higher displacement, and that goes here. And it does that for all of the potential periods of interest and plot all of those. So we are only looking at 1 point in the whole time history. So we are ignoring duration, number of cycles, all of that. We're only looking at the maximum displacement. But it's helpful because it allows us in only 1 figure look at the potential response, the maximum response for many type of buildings, right? Depending on what's their period. This concept of response spectrum is really fundamental in all kind of earthquake engineering analysis. And what it helps us is because, and it's really important because allow us to see, to connect basically the response of a structure to an earthquake the maximum response to what's the maximum force that the structure would feel, right? And the way we do that is that basically we say, well, from the spectrum, we get the maximum displacement if we know the period, right? That's called SD, spectral displacement. And that will change depending on the period. So if we know the period, we go and read the SD from the spectrum plot and multiply that by the stiffness, right? And that will give us what's the maximum value of that FS component, which is the piece of the forces, the one force that the structure feels. Like if you look at down here, the piece that the structure feels is only FS, right? The damping is just how the energy is leaving the system. It's not traveling through the structural elements, so we don't need to worry about that when we are designing or understanding the behavior. And we only need to estimate it accurately. Now what happens is that for many engineers, it's useful to rework this equation, and instead of showing it as stiffness multiplied by the displacement, they want to show it as a mass multiplied an acceleration. So there is a little kind of arithmetic trick here where you can use the equation for the period to kind of rewrite the stiffness as a function of mass and period. And if you do that, you kind of get to this equation down here and call this whole term the 2p over t square multiplied by the spectral displacement, take all of that and name it an acceleration, right? That would be in units of acceleration. This is in units of length, and this is time square. So you have, for example, meters per second square or inches per second square. So an acceleration, which is not exactly the maximum acceleration, right? It's not exactly the maximum acceleration. It's the maximum displacement multiplied by 2p over t square. And depending on how much is damping, that value could be similar to the maximum acceleration or not the same. And then that means that the force that the structure feels could be also denoted as the mass by the pseudo acceleration, right? The SA. And then you can also kind of turn this plot into that, right? Into the maximum pseudo acceleration by different periods. Now, what happens if your structure is not linear, right? All of what we have done before, all of these analysis is kind of relying on the fact that we have a structure that's linear, so the force is proportional to the displacement, period. But if the structure is non-linear, that's not the case anymore, right? There would be a point when the force is not proportional to the displacement anymore, because then you yield and you start having damage in the building, and you can have more intricate responses like cyclics, strength deterioration, stiffness degradation, and all those kind of pinching behavior, all of that kind of cyclic responses that just make the problem not linear, right? So the most basic nonlinear structure is one that still a single degree of freedom, but one that has basically a yielding point, right? So it's linear response, and then as soon as it hits a certain value of force, it would go flat, right? That's called an elastoplastic, perfectly plastic material. And here what we're doing is that we take our single degree of freedom, we run it through, assuming it's elastic. We solve the equation of motion in time, assuming it's elastic, and then we assume it's elastoplastic, it's elastoplastic, elastic, perfectly plastic, and then we get the red response. So notice how the response of the elastic versus the elastoplastic material is significantly different, right? First, the plastic material moves in this example a little bit more, right? From 0.38 to 0.45. The maximum occurs at a different point in time. And notice that the plastic structure now has a permanent displacement, right? When the earthquake ends and starts kind of going back to rest, the structure, it goes to rest not center, but now with a permanent offset. Now, we can also look at what's the time history of the force response, right? And then here you can see that it's the opposite, right? The elastic structure gets to higher values of force compared to the plastic structure, because that one has a cap, right? It cannot resist more than a certain value, right? In this case, 0.15, and it will just get flat there, right? And the consequence is that it's moving more, right? Compared to the elastic structure. Now, here on the right, you can see the kind of comparisons overlaying the hysteresis loop from displacement, displacement by force kind of plots with the elastic structure, of course, is a line. Displacement is always proportional to the force by the stiffness, but with the plastic structure, it's like that until it reaches the, it exceeds the elastic limit, and that way it will just kind of go through this plateau here. And if it tries to go back, it goes back now with a permanent displacement. Now, that same concept is extrapolated to multiple degree of freedoms, right? We just looked at it for a single degree of freedom, but the same thing happens when you have structures that are more complex, right? There are multiple degrees of freedom. And here I just bring a few examples. On the top, you see kind of how the equation really looks almost the same as for the single degree of freedom, but now instead of having scalar numbers for the mass, the acceleration, the damping constant, you have vectors and matrices, right? So you have a mass matrix, you have a damping coefficient matrix, and then you have vectors for the acceleration of the ground, the relative acceleration, and the velocity response. Now, notice how the component here of the force of the structure it is in itself a vector, right? And what happens is that if it's linear, this would be the stiffness matrix multiplied by the displacement vector, right? But if it's not linear, then that relationship, it's a little bit more special, and basically changes depending on what part of the hysteresis curve you are. And in multi-degrees of freedom, you have multiple locations where you can have nonlinearity. And then that treatment of this restoring force that the structure provides to the system, it becomes really important. So here on these three examples, we just show some cases where we're solving this equation of motion for different structural systems, right? So here on the left is a recent project that tried to understand the behavior of wooden houses that had cripple walls, a really typical system for building residential dwellings in California, perhaps before the past 30 years or so. So many residential housing uses this type of structure that's vulnerable to earthquakes, right? And then we assign certain spring elements to capture the nonlinear response. Here is another example down here with a bridge, where we're trying to simulate the nonlinear response of the bridge, including kind of nonlinear springs on the abutments to capture the response of the backfill soil when there is vibration and pounding. Also the nonlinear response of the columns and the deck and all that. And then here on the top right is an example of nonlinear response of high-rise buildings that can have damages and fractures and nonlinear response on the beams, columns, splices, and panel zones, and all the different elements that conform the structural system. Now, nonlinear response history analysis is getting more and more important in engineering practice because of the reasons we outlined at the very beginning, right? It allows engineers to understand the behavior better, and some instances save cost, and in some other instances, perhaps more important, ensure performance, right? We will be able to then make sure that the building will deliver what the building owner or the investor expecting this building or this structure in general, expecting it to deliver. So here are just some guidelines that are used by engineers to perform nonlinear response history analysis. This top couple ones are for design of tall buildings. This one here is the AASHTO for bridges, and down here the ASE 41 for existing buildings, and the ASE 7 for new design. In general, when you want to do a nonlinear response history analysis, the goal that you have in mind is you want to quantify the response. So in terms of acceleration, displacements, forces, that's the response of a structure that's subjected to an external demand that varies with time, right? In this case, we're going to talk about nonlinear response history analysis in the context of earthquakes, right? So, or external demand is an earthquake, but you will always follow these 5 steps. Right, the first step is that you need to build a numerical model of the structure that truly represent the system, the structure you want to analyze, and includes all the possible elements that can fail and where nonlinearity can occur. Right? If you ignore some of those, then your numerical model won't really represent reality. The second step is that you need to obtain a response spectrum target. So in the context of earthquakes, you need to kind of look for what's the load that I want to simulate, right? In this case, would be a ground motion, and the ground motion is described in the context of engineering practice for nonlinear response history analysis with a target spectrum. Then you will select time histories, right? Time histories of ground motions that will be possible representations of that spectrum. So basically what that's saying is you have a target spectrum, but there are many time histories that could give me a similar spectrum. So in step 3, you are selecting those time histories. In step 4, you will solve the equation of motion. That's basically the point where you do the nonlinear response history analysis and compute the displacements, the accelerations, the forces for the building subjected to each of the ground motions time histories that you chose on step 3. And then finally, in step 4, you collect the results and plot them in certain ways that allows you to kind of interpret and understand your results and reach a conclusion, right? Does the building perform well, perform bad, did it move too much? Does it collapse, right? All of those type of questions that are related to performance assessment. So let's walk a little bit through each step. Right, the first step, the build a numerical model. We won't go too much in detail here because this is kind of the big chunk of nonlinear analysis classes. But it's important to kind of have in mind that you have many decisions to make here. Where you decide what numerical model you want to use. If you want to use fancy continuous finite element models, or if you want to use concentrated plastic hinges, or how you want to treat nonlinearity in your model. In your structure, and is it proper for the structure you're working with? Is there data that backups the assumptions you're going to make? All of that's important that you consider there. Then the modeling assumptions, right? Do you want to model this building as a 2D or as a 3D? Do you want to concentrate masses in certain nodes, or you want to distribute them? Are you interested in modeling the gravity system, or only the elements that are most likely to take most of the lateral load? Details like that. And then what software you want to use, right? Do you want to write your own code? You want to use OpenSys, ANSYS, Abacus, ETABS, Perform? There are multiple tools for doing this. And one important thing that in the context of earthquakes is crucial is to know the fundamental period of the building, right? That's something that's really important then for step 3 especially. So now let's look at step 2. Step 2 is obtain the response spectrum target, right? That what's the response spectrum that you want to analyze your building for, right? So this is step 2 and 3 especially, they're both a really big area of active research. At this point here, you have many options to choose. What's your target response spectrum? And that's why those guidelines for engineering practice are important, because they kind of set what the target should be. For specific locations, right? The first thing to kind of keep in mind is that the intensity of an earthquake can be measured in many ways, right? And the response spectrum is just one way to measure the intensity. But you can also measure the intensity in terms of how long the earthquake is. Also in terms of how, what's the PGB, the PGD, the peak ground displacement, the peak ground velocity, peak ground acceleration. And all of that is important to keep in mind. And there are other metrics like the areas intensity and other things like that that are important for measuring the intensity, right? Because the whole idea here is that the earthquake in reality is a time series, right? It's a acceleration time series that we are trying to kind of simplify with a few scalar numbers. And one of those is this response spectrum. Now, for obtaining the response spectrum, you need to respect the seismic hazard, right? That means that you need to consider that what are the faults that are close to your site, how far are they, what's the type of soil that's on your site, and consider all of those pieces to understand and to estimate your target spectrum. But even if you know all of that, you have different options, right? And here, the figure on the right just shows some common options for target spectrum. One is the one that's on the code, the ASCE maximum considered an earthquake, normalized for uniform risk. That's the one shown in black here. You could also have use a conditional mean spectrum target shown in red here, or a uniform hazard spectrum. That's each of those spectrums have like theory, really robust theory behind them. In general terms, the uniform hazard spectrum, what's saying is that the demand on each of the periods from on all periods have the same likelihood of occurring. Whereas the conditional mean spectrum says that, well, it's really unlikely that you have a really low chance. I mean, that you have let's say a 500-year earthquake intensity for all of the periods at the same time. You will likely have it for some periods, and then for the other periods, it's not really that that high of an intensity. Based on observation of previous earthquakes, and it tries to kind of soften that conservatism, and the design kind of event tries to kind of bridge both. If you look at the design kind of target spectrum here, the ASE 7 in chapter 16, you will see that one option for creating the target spectrum is using kind of 5 numbers, right? The SD1, the SDS, which is basically the uniform hazard spectrum ordinates for 1 second and 0.2 seconds. And then the TL here, the period, the long period at which the spectrum changes from being 1 over t, but 1 over t squared. And then 2 more parameters, FA and FB, that control or trying to consider the effects of the soil at the site, right? If you have a really soft kind of clay soil under your building, you will expect the ground motion vibrations to amplify before they get to the surface. So you will have kind of values greater than 1 here. And if you have a rock that's really stiff, then you don't expect much amplification due to the soil layers right under your building. All of these numbers, FA and FB, are tabulated depending on the soil type, and SS and S1 are shown in maps for the entire US, and in other countries, they also have similar maps that you can use to pinpoint what's the specific value that you need for designing a new building. Of course, for simplicity, there are web tools like the ones I'm showing here, the ASC 7 hazard tool, for example, the seismic maps from SEOC that kind of helps you kind of put a pin and get the design inputs easily. Now, the concept of the uniform hazard spectrum, as I was saying, is really interesting because kind of follows rigorously all the probabilistic seismic hazard analysis that's brilliantly done by the USGS. So the idea is that for each period, you can construct a hazard curve, which is it's really a plot that the one you see on the left here. But every value of spectral acceleration has an annual rate of exceedance, right? On a given year, there is a rate of that intensity that could be exceeded, and that annual rate of exceedance depends on the magnitudes of the ground motions that could happen in all the faults around the given site. And you can kind of throw a horizontal line here, which basically is saying what is the spectral acceleration that has the same rate of annual exceedance or return period for all of the periods, right? And that's what you can plot here on the right, the uniform hazard spectrum. So it collects the SA values with the same exceedance rate at different structural periods. All of this is pre-computed, and you can use the USGS hazard tool to get this information right away for any site in the US. Now, how do you select ground motions, right? Let's say you choose one of those targets, you have your target spectrum, and then how do you choose ground motions, right? There are a lot of questions that pop up here, right? The first one is how many ground motions? And then you also need to consider other things beyond the spectrum, right? Like, for example, the site characteristics. If your building is in a subsoil with a lot of, like a deep clay deposit underneath, then most likely it would be better if you select ground motions from past events that also were recorded in similar kind of locations with a lot of soft soil. Then how would you plan to fit the ground motions spectrum with the target spectrum? Are you planning to fit the median, the mean? Do you care about the standard deviation? And then in what period range, right? And then finally, what's the scale factor that you feel comfortable with, right? Because you can think of for example, there is a lot of magnitude 4 earthquakes that happen all the time, right? So you have a lot of records there, but those are not the magnitudes that we are interested in for designing a building, right? We're interested on the magnitude 8s and 9s and the big earthquakes. Those are the NCERs. So if those are the NCERs and we take a ground motion that comes from a magnitude 4, we need to scale it a lot, right? Multiply it by 30 or 40 or 50. And then how realistic is that? So then you need to kind of keep that in mind. Then there are different kind of algorithms for selecting the ground motions. There are 3 kind of leading ones. The one that's specified on the code, ASE 7, that's the one you have the opportunity to use in this module. But there are other ones, conditional spectrum or generalized conditional intensity measure that allows you to consider other types of intensities beyond the spectral, like duration, things like that. And there are other factors to keep in mind, right? If you're really close to a fault, maybe the pulse period is important. And if you have a seismic isolated building, there are other factors that come into play when you want to select ground motions. Now, if we narrow down on looking at the ASE 7 guidelines, it just sets basically these 7 things, right? First thing is you need to select 11 ground motions. They should have a similar shape to the target spectrum, and that each ground motion should be scaled such that the average, the mean of all the ground motions is equal or greater than 90% the target between 0.2 and 1.5 times the fundamental period of the building. And then there's other requirements like select from the same tectonic regimes, or like if you are, for example, in San Francisco, where the San Andreas Fault dominates the hazard, strike slip type of fault, then you should select ground motions that come from strike slip faults or ruptures. Then also the ground motions will be selected from events with consistent magnitudes, what we were talking earlier. If you're in near site, then you need to consider directivity effects and pulses and things like that. And then if you're doing 3D models, you need to select pairs of ground motions, and that's very important. So how do you select ground motions that can fulfill that criteria? Well, you have a suite of optimization algorithms to do that. But basically, the idea is that you calculate the spectrum for your building. I mean, for each of the ground motions candidates. So basically, you start with a pool of candidate ground motions, right? Thousands of ground motions that have been recorded. You calculate the spectrum for each of those ground motions and then compare it to your target, right? And then start scaling, you take each of those pool of each candidate ground motions, scale it so that it's the closest possible to your target ground motion, and you calculate the error, right? Which is basically, for all of the periods in the period range of interest, you compare your target with the ground motion that you have, that you're evaluating the candidate, you get a value of error. And then do that for many and select the ones that, the 11 ones that do the best, right? And fit on that moderate scale factor and all that. Again, keep in mind that if you have a 3D model, you need to select pairs of ground motions or even sets of ground motions, including vertical acceleration, if you want to include that in your model. And then that kind of requires a little bit more care, that it's kind of out of the scope of this video. Now, where can you find that pool of candidate ground motions? Well, there are many options online, and one that's really useful is the peer database, the ground motion database that you can reach on this, on this link here. This is a database that took many ground motions from around the world and in the raw state, so just like they were recorded by the instruments, and processed them to make them useful for nonlinear time history analysis. That processing, in general terms, is basically taking the raw data and applying some corrections, like filtering really high and really low frequencies that are not really frequencies from the ground motions, but noise on the signal, and maybe doing some baseline corrections if this instrument wasn't centered in 0, so force it to be centered on 0, and applying the constants of the instrument to go from whatever electrical measure what it had to acceleration. So all of that work is done uniformly by the peer, or was done by the peer center, and make this publicly available. So you need to basically create a user profile here on this link, and that will give you the opportunity to access the thousands of ground motions. Then the fourth step is to perform nonlinear time history analysis. So you already have your model, you already have your ground motions, and then for each of those ground motions, you perform the model. And here, depending on which software you use, you're able to kind of choose the solution algorithm of the equation of motion. If you want an implicit or an explicit type of algorithm, you also need to define your damping model, right? If you have a multi-degree of freedom, you need to define that damping matrix. And the damping matrix could be defined assuming model damping or Rayleigh damping, those are the leading types of damping models. But there are other type of models like classical damping and things like that that are more detailed about how you can capture that aspect for multi-degree of freedom problems. And then you also have to set some convergence criteria, right? How you want to quantify error? What's the time step in your analysis? And how many iterations you want to accept to achieve convergence and continue the analysis to the next time step. And then finally, you collect all the results and you organize them. The typical kind of outputs that are of interest for structural analysis are peak deformations, or in this case, interstory drift, peak floor accelerations, and element forces, right, for capacity design of elements. And you can plot them in figures like this, for example, where you have the story on the vertical axis and you have the interstory drift or the floor acceleration on the horizontal axis, and you have in gray each of the ground motions you analyze, and you overlay some statistics on top to kind of understand what's the spread and what's the mean response and how that compares across ground motions. The example you have the opportunity to look and perform in the next video tries to go through all of these 5 steps using OpenSeas for building a numerical model, using EEUQ for getting the target spectrum, selecting the ground motions, and performing the nonlinear response history analysis, and then Python through Google Colab to kind of collect the results and show some of the or create figures that allow you to inspect the results a little bit better. So with that, I invite you to go to the next video and work on the example. Thank you so much.